I think already you have come across in chemistry. Let's study this. Let's a bit in detail. Okay, there's a wavelength. I'll plot it, and there's a intensity. Intensity of radiation, watt per meter square. Now, for different bodies, for a given body at various temperatures, I'll plot it. Then what I notice is the curve. There's a temperature T1, T2, T3, T4. Lambda 1, lambda 2, lambda 3, lambda 4. Okay, what actually we are studying? So let me take a body of any shape. Let me take a sphere so that 4 pi r square I can write it. Huh? Okay, this is a sphere of radius r. This of a black body is what I'm studying. Okay, this is a perfect black body. So it's having a radius r. Then what I do, let it be at temperature T1. Then what it does, it's isolated body. So it will give out radiation. It will emit. So why do it will give emission? Why it will radiate? Why it will give out heat energy? Why do it give out heat in the form of EM wave? Because of temperature, the charged particles inside that material, they'll vibrate and the charged particle get accelerated. Due to acceleration of charged particle, what happen? EM wave will be generated. That EM wave, what happen is what we'll call that as radiation. That's all. It'll give out. Okay, now how much of energy given out by it? According to Stephen's law, power is equal to what we write? Sigma A T to power of 4. So what is the temperature of the body? Based on that, what is going to emit power? What is this? This is a power. Energy per unit time. This will have a units watt, sigma, Stephen's constant, area, 4 pi r square. Okay, next question. Let's measure the wavelength. I'm interested to know the wavelength. What are the, I'll look at the radiation. So what is this red color like this? Emitted radiation. Okay, emitted energy, or you can call like anything spectrum, or so like a energy emitted or emitted, whatever that one. I'll go and check the wavelength. What I notice is like I will get all the wavelengths from the lowest value. Don't take zero, not possible, to the highest value. So a body at a given temperature will emit, will give out radiation of all wavelength. They're the first thing. Point wise, I'll write it. A body at a given temperature emits radiation of all wavelength. Means now you look at yourself, your body, that one. What is the temperature of your body? Shall we put around 36 degrees Celsius, 36 to 37? Are you giving out radiation of all wavelength? Yes, all wavelength. Sir, I'm emitting even X-rays. Yes, you are emitting all radiation of all wavelength. So I'm not going for upper spectrum here. Yes, in fact, you are going to emit radiation. And when I compare the intensity of that radiation, what do you mean by intensity? Energy per unit area per unit time, like that. When I compare the intensity, for one specific wavelength, the intensity will be maximum. So now let me increase the temperature of the body. Let me increase the temperature of the body. Then at temperature T2, what will do? Then the body again will give out radiation of all wavelength, 0 to infinity, better say. Then what I say that and one specific wavelength, the intensity will be maximum. So don't say that here also. At this wavelength also there'll be intensity. But at one specific wavelength, what happens? The intensity is maximum. Again, I'll increase the temperature to T3. Then what I see is that, what I notice is that it will give out radiation of all wavelengths now. Again, at one particular wavelength, the intensity is maximum. Now, what Wien's he has seen is that these two are related, is telling. So what is telling? The product of the wavelength lambda into T is equal to constant, where B is called as Wien's constant is telling. Okay, I think already you know a little bit idea of this one. So what is this lambda in T now? What we should call this lambda in T? Okay, let me find out the value. This will be, I think, 2.89. To up to 2 decimal place, I'm able to remember. Wien's constant, no? Wavelength lambda meter, temperature Kelvin. Okay, there's a value of Wien's constant. The relation between this lambda 1 and T1 is what is giving. So here we can write it. And so on. So what is this wavelength? What I should call? What we should call? The wavelength at which the intensity of radiation will be maximum. Say it will give out the radiation of all wavelength. At one specific wavelength, the intensity will be maximum. That is called like a maximum spectral radiancy. The wavelength at which the intensity will be maximum, or this is called like a maximum spectral radiancy, it is called as the wavelength corresponding to maximum spectral radiancy. So how in books they're defined? What is lambda? Wavelength corresponding for maximum spectral radiancy. So what Wien's is telling, as I rise the temperature of the body, the wavelength corresponding to maximum spectral radiancy or the wavelength corresponding to maximum intensity, it will shift, it will take the lower values. It will take the lower values. So let's take example like, okay, I'll take the iron rod, especially when it is red hot, it will have temperature, say like a T1 and lambda 1. Further, when I eat it up, it will become orange, no? So it will be in red color. Now, when it is in orange color, it will have temperature T2. When it becomes yellowish, I think I'll put lambda O, T2, TO. Let me use proportional symbols. When it is yellowish, temperature will be red color. Now, which will be hot? In which case, the iron rod will be very hot. I think when it is, we know temperature TR greater than TO greater than T. When iron rod, when it is in yellowish color, I think it will be in molten state. When it is in yellowish color, So what happens? It will be at higher temperature than when it is at orange or when it is in red color. The reason for that, if I go and measure the temperature, no, when it appears as yellow, what will happen? It will be at higher temperature. Then why do it appear yellow? Next question comes, why do it appear yellow? Here what happens? When it is red color, when the iron rod is red hot, it will emit radiation of all wavelength. Then the radiation corresponding to red color wavelength, it will have maximum intensity. That's why the iron rod will appear as a red dot. Don't think that this iron rod will emit only red color wavelength. It will emit all the wavelength of all radiation starting from 0 to infinity, better say. But why do it appear red? Because the wavelength corresponding to red color will have maximum intensity. So the eye will perceive that it is red. But what when it is emitting also the blue color, yellow color, violet, indigo, X-rays, radio waves, microwaves, all the radiations it is giving out. It is giving out wavelength of all radiation. But since the intensity corresponding to red color wavelength is maximum, that's why it will appear red color. Then further I'll increase temperature. It'll become orange. Then why did it appear orange? It will give out radiation of all wavelength, red color, yellow, blue, indigo, microwave, X-rays, lower radio frequencies, everything that one. Then why it will appear orange? Because the intensity corresponding to orange wavelength will be maximum. That's why it will appear orange. Are you getting no? So don't think that when it is a red color, it will emit only red color wavelength. It will emit all. This is what basically a property of a body. Because at a given temperature, a given body radiate will give out energy, will give out radiation corresponding to all wavelength. I think this is what already in the beginning we have put it. All bodies radiate at all temperature. Further, what we have to put it like, at a given temperature, a given body will give out radiation of all wavelength. There's a one next important. A body at a given temperature emits radiation of all wavelength. I think I already put it. Don't think that only lambda 1 it will emit. You can see this curve. Now, as I increase temperature, according to Stephen's law, if I increase temperature, the power emitted increases. So therefore, here, the area under the curve will increase. What do you mean by intensity? Power by area is intensity, no? Power by this area is what? Intensity. So any interpretation of graph, anything shall we interpret related to graph? Anybody? The area under the curve, what it will give?
B, sir.
What will happen B? I'm not getting. This area under the curve, what will give? Total energy radiated by a body. That's all, no? The area under the curve, because you see that if I increase temperature, the total power radiated will increase. So area under the curve is also increasing. So therefore, the area under the curve, what it will signify? The total energy radiated by a body. So next point, okay, I think all the points will put it at one place. Next one. Area under the curve is proportional to total energy radiated by a body. So therefore, as I increase the temperature of a body, what will happen to the total power radiated body will increase. The area under the curve is increasing. Then what will happen to the wavelength at which intensity is maximum? We'll take the lower values. I think that's what this particular Wien's displacement law is telling. So what is telling is like, as you increase temperature, lambda will decrease. B is a constant, no? Wien's displacement is a constant. As you increase temperature, lambda will decrease. What is lambda? The intensity for which, the wavelength for which intensity is maximum. We are not bothered. Say like a temperature T1, what is this wavelength? We are not bothered. I'll give one more graph so that it'll be easy for you. Because lambda 1, lambda 2, you are getting confusion. Now, if this is a curve, let me plot the curve. Now, please, only one. This is what t lambda naught. If you want, you write it. This is a wavelength. This is intensity. Okay, this lambda naught and t are related by Wien's law. We don't know anything about this one, sir. How this wavelength and t are related? We don't have anything. Only the wavelength for which intensity is maximum and the temperature of body are related by Wien's displacement law. Able to get this one? So what is the Wien's displacement? It will give us relationship between the temperature of body and the wavelength corresponding for maximum intensity. You see that particular body, it will emit wavelengths very high energetic photons, or you can say a very low wavelength, and also it will give out radiation of very large wavelength. A given body will give out radiation of all wavelength at a given temperature. Not, don't think that only lambda naught. Why do it appear that specific color? Because this particular, for this wavelength, the intensity will be maximum. So therefore, the I will feel as if only this wavelength is entering into I. The perception of I will be like that. If you look at the red dot iron, do you think that only red color wavelength it is emitting? No, it is giving out radiation of all wavelength. But the red color wavelength will have more intensity. They'll be more dominant. That's why it will appear red color. Able to understand the meaning of this particular curve. At a given temperature, a body gives out radiation of all wavelength. Then why do it appear specific color? Because the intensity for the wavelength for which intensity is maximum, that particular wavelength will be dominating. So that will determine the color of a body. So why the uh, like a iron rod, red dot iron rod, why do we apply red? If you increase further temperature, become orange. If you further increase temperature, it will become yellowish. So what is the meaning of that? So we can use Wien's displacement law. Like this, we have a stars like. Okay, let's go for stars. So this is a stars will be spherical. So since we got from childhood, we got habituated to show stars like this, twinkling, no? Because of that diffraction of pen, they will appear like a twinkling, but actually there is sphericals, that one, spherical in shape. Again, don't scold me that physics teacher don't know that star he has drawn. Actually, it's like a sun only, no? So spherical, that one. So we got habituated from childhood. Okay, I'm just showing that one. Okay, like this, I do have 3 stars. No. Which star, temperature of which star will be more? This is T1, T2, T3. This blue, the star which is appearing blue color, will it emit radiation of only blue color? No, it will give out radiation of all wavelength. But the intensity will be maximum for blue color wavelength. That's why it is appearing blue. Next we have red color. Next we have yellow color. Can we categorize the temperatures? So we know Vibgyor, violet, indigo, blue, green, yellow, orange. The wavelength we do write like this, no? Lambda V, lambda I, lambda B, lambda, lambda of green. Okay, this, okay, now lambda of blue will be greater than, will be less than that of yellow, will be less than that of red. Or if you compare lambda R will be greater than lambda Y greater than lambda B. Apply Wien's displacement law. Lambda R, okay, lambda R T3, lambda red color T2, no? Yeah. lambda y T3, then lambda blue T1. Can you say anything about this temperatures? Which will be at high temperature? Blue color star, yellow color star, or red color star?
Blue.
Blue, no? So T1 greater than T3 greater than T2. Intentionally, I'm writing like a T2, T3 like this. Okay, no? So by looking at the appearance of that particular body, what happened? We can determine what can be the temperature of the bodies. There's basically a Stephen's law and the Wien's displacement law. So what are the few important things like as we increase the temperature of the body? So with this, what we can write it here. So from here, what we can write it, lambda 1, lambda 4, lambda 3, lambda 2 less than lambda 1. What about temperature? T4 greater than T3 greater than T2 greater than T1. Will I agree? The comparisons for a given body here, this is spectrum for a given, not different bodies, for a given body only. As I rise this temperature, the curve will be like this, and the wavelength for which intensity maximum, that will shift. So that's why the name word displacement law, Wien's displacement law. All of you, displacement. Are you looking at this lambda? As you rise temperature, what will happen to lambda? What is this lambda? The wavelength for which intensity is maximum, or wavelength corresponding to maximum spectral radiancy. It will take the lower values. So it's getting displaced. This one. Okay, next question comes. Why a body at a given temperature, this is, what is the spectrum? This is again spectrum for a body at a given temperature. Why the intensity will be minimum for, so like a shorter wavelength? Why intensity is again minimum for longer wavelength? Why the intensity is maximum only for one specific wavelength? Okay, what is this? According to Wien's displacement law, only this, the wavelength corresponding to maximum intensity and temperature of body, what when they're related. What is T? I should, for a given temperature of body. And what is lambda? The wavelength corresponding for maximum spectral radiancy. Only the Wien's displacement law is able to relate this lambda naught and T. It is unable to relate this lambda, and this T. Why the curve like this? No, we don't have explanation. Classical mechanics is unable to explain why a body will, why the intensity will be very low for shorter wavelength. Why the intensity is very low again for longer wavelength. Then again, why the intensity is maximum only one at specific wavelength. Okay, that one, the classical mechanics, they tried a lot. Rayleigh-Jeans law was able to explain this. Kirchhoff's Rayleigh law was able to explain this. Wien's displacement law was able to explain only this. They tried the physics what we know, and finally they were unable to conclude. Then Planck's radiation law came. I think all of you study Planck's law, chemistry. Am I right? Yes or no?
Yes, sir.
Planck's radiation law. Why the Planck's radiation law? Why Planck should come and give radiation law? He's saying energy is quantity equal to NHF. With the help of Planck's radiation law, we are able to explain the curve. So it's a quantum mechanics as begun, the basics of quantum mechanics. So definitely what happened, student ask himself, okay, sir, this wavelength and temperature of body, any relationship? No, we don't have any suitable equation. And if I write any equation, it is valid only for here. It is unable to explain this. Wien's displacement, only this lambda not T. Rayleigh-Jeans law was able to explain only this one. Kirchhoff's Rayleigh law was able to explain only this. We don't have any law which will explain the total curve. So the classical mechanics, what we are studying is classical mechanics, has to put a question mark. We are able to explain why the curve like this. You should ask this question to physics teacher. So why the curve like this? Physics teachers will reply. What will reply? Okay, you after writing advanced exam, okay, give me 1 month time. Okay, that one I'll explain quantum mechanics. Using quantum mechanics, I'll explain it. So these are all unanswered things in our syllabus. So gradually what happen? We will touch a sections or will touch a syllabus where we'll end up with a question mark. That is what the classical mechanics. So what is the how we end up our classical mechanics with a question mark? We don't know. Finish over. Oh, sir, then what about these answers? These answers are given by quantum mechanics. Classical mechanics will stop here only. Like that, you can see that once you enter into second year syllabus, no, every topic will end up with, say, especially modern physics. When you enter modern physics, no, there are the as a, like a wave optics. Every topic what will end up with a question mark. If I end up with a question mark, yes, you studied classical mechanics. If you feel that okay, sir taught everything, very nice, superb, then what happened? I didn't explain anything. So here what happened? We should end up with a question mark. The physics, what we know. See, I don't have any equation. Stephen's law, can it explain why? No. Stephen's law will tell that it will give out energy, that's all. The power radiated depends on area and temperature, that's all. Wien's law is able to tell only between these two relationship. Other laws are there. One law will be this, one law will be this. But we don't have any satisfactory law which will explain the total curve. So what is the problem? Yes, there's a limitation with this knowledge itself, the classical physics itself, the classical mechanics it is called as, it's having its own limitations. That's why what happened? To overcome this, a new branch of physics is brought, quantum mechanics. That's why we have to learn quantum mechanics to learn the higher level things. Okay, it's not there for our syllabus with this one. So what is your class 2 level? Till our syllabus is based on only classical physics or classical mechanics it is called as. What all you are going to learn at higher level next in engineering, no, that will be quantum mechanics. Fine. Okay, a student has to really, it will give out a radiation of all wavelength. Why here intensity less? Why intensity is less? Why only here more? We don't have explanation. Getting some idea? This one. So tomorrow we'll discuss the numericals straight away. This is about the theoretical. If you want, you can read and work out some problems based on this. Stephen's law and Wien's displacement. Just only formula based, nothing is there. Tomorrow, Newton's laws of cooling, one formula will come. These are the only three formulas which are there. The whole topic revolves around these ideas. Okay, tomorrow I'll continue from here.